Welcome back. So in the last video, we kind of summarized our work on estimating the area under a curve by giving a special name to that's the sum of all the rectangles that we draw under the curve, whether they're left rectangles like the ones in this picture, or right sums, or midpoint sums. The basic premise is the same every time. Each rectangle has a width, and we usually denote that with the change of x. So on each of these subintervals, there's a width, delta x, and each rectangle has a height, whether it's drawn at the left endpoint or the right endpoint or somewhere else. Each rectangle has a height, and it is measured by the value of the function. And so the number we put into the function to get the height might be the left point, the right point, or the midpoint, or some other value in the interval. It doesn't really matter though, so my sum of all the rectangles would be each rectangle's height times each rectangle's width, and then adding them together gives an approximate area under the curve. And so because this is used not just for the area under a curve, but it'll have lots of other applications, and it's so common, this type of summation, this type of sum has a special name. It's just named after someone, and we call it a Riemann sum. And then we also talked about that if I were wanting to improve this and get a better approximation of the area, I just want to increase the number of rectangles. And so we actually are going to have a special symbol for that notion. And that is, this next definition shows that if I take that Riemann sum, in other words, thinking of it right now as the sum that defines the area of the curve, but I let the number of rectangles become really, really large and infinitely large, then we get that limit should produce the area under the curve. And we're from now on going to denote that with this special symbol right here. We call it the definite integral symbol. And notice the notation over here reminds us a lot of our Riemann sum. We have the function, just like we do here, and we have dx instead of delta x. Okay, but then this special symbol here we call the definite integral symbol, and it replaces the summation notation because it also includes the interval a to b. Okay, so from now on, for just a little while, we want to think of this definite integral symbol as a way to describe the area under the curve. So if I see a symbol like this, I could immediately picture my function on the interval a to b. And then the definite integral symbol represents the value of the area that I would shade down to the x-axis. In the last video, we also talked about the fact that if your function were to dip below for a while, so maybe this is your a and this is your b, then the value of the integral might not be the grand total of the area, but the net area, which means like the portion of the function that is above the x-axis has a positive integral value, and the portion that is below the x-axis has a negative integral value, etc. Okay, so what we want to focus on today is just kind of interchanging between the notation of the definite integral and the drawing of that in terms of a region. And if the region is simple enough, we could actually evaluate the numerical value of the definite integral. That's what we're going to try and do today. So what I have here is a definite integral symbol, and what we're going to do is make a drawing and see if I can evaluate the value of this integral by interpreting it as area. Well, first I'm going to break down the symbol a little bit. Just remember that the definite integral symbol contains lots of useful information. It contains the interval on the x-axis, a and b. It also contains the function f of x inside it. So I can dissect this one and say, well, this is referring to the function f of x equals 4, and it's on the interval 0, 3. Okay, so we're actually going to draw this. On the x-axis, I'm going to start at 0. I'm going to go all the way to 3. And on the y scale, since this is just the function f of x equals 4, I'm going to go to 4. I'm going to draw in green. Here's the graph, nice simple horizontal line. This is f of x equals 4. And interpreting this integral as area, I'm going to draw a vertical line here at x equals 3. And I'm going to take my highlighter and I'm just going to shade all this in. Okay, so I'm just going to So if we interpret the definite integral as the area under the curve, well, all I see is that this formed a rectangle that is 3 units across and 4 units high. And so the numerical value of this integral 0 to 3 of 4, the numerical value is simply 12 because that's what the region's area is. It's a 4 by 3 rectangle. So the numerical value simply is 12. So let's try it again with this integral. This is the function x plus 1. And the interval this time is 1 to 5. I'm going to do a quick sketch of this. Hopefully you know this is going to form a line. We're going to start at 1. We're going to end it at x equals 5. And it looks like for the y scale, we're going to have to go up as high as 6. So just picking a few key points, at x equals 1, f of 1 would be 2. And at x equals 5, f of 5 would be 6. And this would just form a line through here. But now I want to section it off by drawing vertical lines on 1 and 5. And I'll grab my highlighter again and we will just shade this in. And now the numerical value of this integral is the actual area of the shaded region. So I encourage you to pause the video here and try and find that area yourself before I talk through it. Okay, well, a common way that most students would see this one is you might have done this too. If I just draw a horizontal line right here for a minute, I can actually break this shape into 2 shapes, a rectangle and a triangle. So noting that this upper left corner was the point 1, 2, this rectangle has a height of 2, and going across it, notice we're going from 1 on the x scale to 5, so that's a distance of 4. Okay, so since this is a 2 by 4 rectangle, this area is 8. So I'm going to start with that, and then I'm going to tackle this triangle. It's also 4 across this way, but now if I look here, these 2 points will help. We're going from the height x equals 2 to a height y equals 2 and then y equals 6. So we're going down from 6 to 2, so that's a distance of 4. So this triangle is 4 by 4, but to take a triangle you take half of 4 by 4, so this is actually going to be 8 also. And so my integral from 1 to 5, x plus 1, the grand total is 16 because that is what the area is that I found there. Okay, the last task is, let's try this the other way. I will draw the regions and I'd like to see if we can write and just express this region as an indefinite integral. I'm not going to ask you to actually solve what the numerical value is, but I'm going to tackle the blue part first. And I've been giving this as the graph of y equals 2x plus 1. It's on there, but I'm going to write it as y equals just for now also. And this blue interval begins at the vertical line where x equals 0 and then ends at the boundary where x equals 2. So I would interpret this blue area to be the integral 0 to 2 of the function 2x plus 1. And we always put that dx at the end. So just to express that as an integral, that's how I would do it. Now for the red though, it's different, a little different, because we haven't shaded below the line to the x-axis. It's actually above the line up until this point 2, 5, and we just drew across. So I can think of a couple of ways we might want to attack the area in red. One way, which is kind of neat, is to see that the two shapes combined made a rectangle. And so it's pretty easy to determine that that rectangle that I'm kind of going around here has an area of 10, because it's 5 high and 2 across. And so if I took the area of the rectangle and just subtracted the blue area, I would get the red. So that's one way. That's one way to handle it. But there's another way, and it only requires me to use an integral, but not this one. Think of it this way. If you turn your head kind of to the right and look at it this way, think of this as the independent variable, and then we graph the x. Okay. So if you think of it that way, and you could almost think of it like if you were doing a stack of rectangles like a Riemann sum, you could actually draw rectangles this way that connect back down to the y-axis. I'm doing it very crudely here, but you see? So in this construction, this little width is the delta y, and this is a function of y, because we're picking the x, we're picking the y, and we're solving for x across this way. So what we're going to end up doing is I'm going to write this equation in terms of y by solving for x, right? So if I took y minus 1, it would be equal to 2x, and that would make x equal to y minus 1 over 2. And I could call that now f of y. I'm actually going to change it to g of y just so I don't use the same name again. So I could probably do that down here too. So g of y, the function of y, is really y minus 1 over 2. And notice that in this region, the y values go from 1 to 5. So an alternate way to express the red area here would be as another definite integral, but this time I'm going to put my function of y in there. And the interval is from 1 to 5. So this is an alternate way with a single integral to express that pink area there, the red one, and that is, think of it as we're graphing, instead of saying under it, meaning toward the x-axis, think of under as meaning toward the y-axis, which means you've got to have the function in terms of y and the limits of the integral, the interval being 1 to 5. Okay. Well, this will be the end of this video. This should help you with a good chunk of the exercises. We'll see you back on the next video to talk about some of the properties of definite integrals. And that'll be something you work on the next e-learning day.